Hi everyone. This is the fourth video in the heap series, and in this video we're going to talk about removing from a binary heap. Now, remember that a binary heap is first of all a complete binary tree where heap order property is maintained. So when we do remove, we want both of these to be true. We want the tree to stay complete. We want heap order to be maintained. So now, with that in mind, let's take a look at what removing from a binary heap means. So first of all, similar to a queue, we're not interested in removing just any old value from a heap. We're not erasing n. We're not erasing x. We are erasing the highest priority item. Okay, so in a min heap, this would be the smallest item. In the max heap, this will be the biggest item. But either way, what we want is the thing with the highest priority. This is what we want to get rid of. Now, that highest priority item will always be in the root of the tree. Okay, so this is really important. The value we want to get rid of comes from the root. But the node that we get rid of is not in the root, okay? And this concept is really different from what we've done before when we talked about linked lists. So if we talk about erasing a certain value from a linked list, we typically go and find that value and then we get rid of the node, right? The node contains the value we want to get rid of. So getting rid of the node gets rid of the value. This is not what we do here. We do not get rid of the node that contains the value. We get rid of the value and we put something else into that node. Okay, the node we want to get rid of is the one that is at the bottom level rightmost. Why? Because our tree has to stay complete. So the way that our algorithm works is going to be a little bit different. So here is a picture. So here we have two pictures of a heap. Here is a heap that has 10 nodes in it on the left over here. And here is a heap with 9 nodes. Now, this is the proper shape of a tree with 10 nodes and a proper shape with a tree with 9 nodes, okay? Because our tree has to be complete. This is the only shape that is allowed, okay? It's not like if I have 10 nodes, I can have 10 nodes anywhere I want. This is the exact 10 nodes that I need for it to be complete. The root of the tree is here. And it contains the number I want to get rid of because that is the highest priority item. That's where it is. Now, if I start off with 10 values in the heap and I get rid of one of them, do a pop, what do I end up with? Well, I end up with 9 values, right? But we say that a heap that has 9 values in it should look like this one on the right. So how do I make the left-hand side look like the right-hand side? Well, I have to get rid of this node down here. Then it will be correct, right? So because of how we have to get rid of things, the node that we remove and the value we want to remove are two different things. Our algorithm has to reflect that. We can't just, get rid of the root. If I got rid of the root, I would end up with 2 trees, right? You can't get rid of a root node because it's the one thing that links everything else up. Get rid of it, now I have 2 trees. So can't do that. You have to actually maintain that node, okay? Now, what does this all mean? Let's take a look at our algorithm. So the algorithm for removing a node goes like this. We're going to store the bottom rightmost node's value into a temporary. We're going to delete the bottom rightmost node because that's the node we have to get rid of for completeness. We empty out the root, okay, making the root an empty node. And then we try to put the value that was stored into our temp into that empty node. And if it's okay, if heap order is maintained, great, put it in. If it's not, we take the higher priority child, pull it up into the empty node, making the higher priority child's old node empty. Note that this can cause a value to go from one side of the tree to the other. That's okay. We didn't say that if you start on the left, you can't go to the right, okay? So we just simply keep pulling up the higher priority child until we find a place to put our value. At worst, this will be in a leaf node. Because once we hit a leaf node, there is no more children to look at, so this node must be the place we put it. So let's do an example. So here is our heap, and our heap right now looks like this. So if we follow the algorithm, okay, so let me just adjust this just a touch. So I'm going to I'm going to put the algorithm here so that's easy for us to see. Here's the algorithm, okay? Here's the step by step. How do I actually apply this algorithm then? How do I make this algorithm work? Let me just make this a touch smaller. Okay, here we go. So now, when we remove, we're going to start by creating a temporary. Temporary is 15. We're going to take the temporary and we're going to move, so we're going to take the value in the bottom rightmost node, put it into our temporary. So this is our temp. Then we get rid of the bottom rightmost node. Now we empty out the root, so we don't get rid of the node, we just mark it as empty. We record the fact that it's empty, is available to use. And now we try to put 15 into that node. Can I do it? No, because both 3 and 5 are higher priority than 15. So I take the higher priority child and I move it up into this node. Oops, right here. Can I put 15 into this empty node? The answer is still no. 15 is higher priority than 20, but it is not higher priority than 10. So this is actually a possibility as I'm looking at this. So 15 can't go into the spot because even though it's okay with 20, it is not okay with the 10. So what do we do? Well, we move the higher priority child, which would be 10 in this case, up. Can I put 15 into this empty spot that just opened up? The answer is yes, because 15 is higher priority than 20. So take the 15, move it back into this position, and we are good. So this is how we do a remove, okay? So now what I want you to do is I want you to take this tree here, okay? I want you to take this. I want you to try to pop 3 times off of this tree. What do you get? Okay, so if you perform pop 3 times, what is the final tree that you get? Use the same algorithm, okay? So draw a picture, okay, and just draw what your results are after each pop. I'm going to pause the video now. I'm going to count to 5 and then I will show you the answer, okay? But pause the video and do it yourself first, okay? 5, 4, 3, 2, 1. Okay, so hopefully you actually paused and did it. So now let's take a look at the answer. So check your answers here. So the first pop is going to do the following. We're going to take the number 25. We are going to move it into the temporary. We're going to get rid of this node right here. The number that goes away is 3. Now, can I put 25 into the spot that's now available? The answer is no, because 5 and 10 are both higher priority. So we move the 5 up because 5 was the higher priority child. Notice that I don't have to move it. When I'm moving the 5 up, notice that I'm now going down the right-hand side of the tree. The 25, remember, was at the left-hand side. So I'm now going down the right-hand side. That's perfectly okay. There's nothing wrong with doing that, okay? So just keep this in mind. This is how we're doing it. Can I put 25 into here? The answer is no, that's still not valid because 8 and 19 are both still higher priority. Who do I pull up? Well, 8 is higher priority than 9, so we're going to move the 8 up into this position. So can I put 25 into here? Well, it's a leaf node, so sure, of course, why not? We're done. Okay, so this is how we do 1 pop. Now, if we pop again, okay, bottom rightmost node is now 19. So 19, so this is after 1 pop, this is what we have. Okay, so to make it a little bit clearer, I'm gonna just take this. Now we do it again. Okay, so this is our second pop. Where do we go from here? So we do exactly the same algorithm as before. Okay, I just want to make it a little bit bigger. It's a little bit easier to manipulate. Here's our temp. Take the bottom rightmost node, which is 19. Okay, so even though 25 is lower priority, bottom rightmost, like literally go left to right. Here's left, here's right. Whoever's further to the right, take that one. Okay, take this, grab it, put it into the temporary. Erase the bottom rightmost node. That would be this one right here. Erase it. Empty out the root. That would be the 5. The 5 is now gone. Can I put 19 into here? No, because both 8 and 10 are higher priority. So I'm going to move the 8 up into the root. Oops. Take the 8, move it up. And now, can I put 19 into that spot? The answer is yes, because 19 is higher priority than 25. There's no right child to check against, so we're good. So this is after 2 pops. This is what you have. Okay? Now, what about third pop, right? What happens after the third pop? So here's our tree. Here's what we have. Okay, so if we pop again, what do we get? So again, using a temporary, take the bottom rightmost value, this time is 25 again, we put it into here. Erase that node. Empty out the root, but don't get rid of the node. Can we put 25 in there? The answer is no. So we're going to move the 10 up into the root here. Can I put 15 into that empty spot? Or sorry, 25 into that empty spot? The answer is still no. 25 is actually lower priority than both 15 and 20. So between 15 and 20, who's higher priority? That would be 15. So move 15 up into its parent. So 15 ends up being put, 15 ends up being put here. And 25 ends up here because this is a leaf node, so we can always put it in. And that's after 3 pops. Okay, so you can see that it does move around quite a bit. But if we take a look at how this works, a pop is still order n. Okay, so this is what you should have at the end. Sorry, order log n. So what did we do with a pop? Well, when we're doing a pop, we empty out the root node, right? The root node gets emptied. And then we continuously try to look for a place to put that node that we have stored away into the temporary. So this spot is empty at the beginning. We try to put it here. Now, what if it can't? Well, we try to put it here. If it can't, well, we try to put it here. And if it can't, well, we can try to put it here, whichever left or right depends on the actual value. But the worst case scenario is that our empty spot starts at the root and moves it away from the root all the way down the tree. Notice we don't look left or right. We only look going down. We only say, hey, children, which one is higher priority? You need to move up, kind of thing, right? So our empty spot, if you think about it as a movement of empty spots, the empty spot just moves down the list. It doesn't actually move sideways, which means that it takes log n moves of empty spot to complete to complete the pop function. So because of that, it's kind of nice because it means that we don't have to compare everything. So the more things we have, the less we have to compare relative to the size of the table. So something to keep in mind, okay? Pop is doable in log n time. That's nice, okay? So remember when this whole thing started, we had push, pop, and front, right? so when we first talked about priority queues, we said, okay, we have these three functions we care about: pushing the data in, popping, and front. And when we were just talking about sorted arrays and linked lists, we couldn't get it to a situation where all of them were better than n. But now we actually can show that we can, because our push, remember, was log n. Our pop is obviously log n because we're moving that empty spot down the tree. And front just returns the highest priority item, which is at the root. So that's easy to access because we always have access to the root. So that's actually going to be O1. So what this means is that if we go back to using a binary heap, we can now say that a push data, this is going to cost us O log n. Pop is O log n as well. And finally, front, that one is constant, O1. So this is great because this actually means that our binary heap is actually fast if we implement it using, sorry, our priority queue can be fast if we use a binary heap to implement our priority queue, okay? So this is why we do it, because this is actually a faster data structure to use, okay? Now, in the next video, we're going to talk about a slightly different algorithm called, uh, we're going to talk about make heap. So what if we already have things that are in a tree form, like a complete tree form, and we just wanted to create a heap out of it? And then we're going to talk about implementation and so on. And then we're going to talk about heap sort in the last video. Okay, so that's it for now. Okay, see you soon.